purple cyanobacteria seem pretty well adapted to life around these redder stars.
Hello, and welcome back to another episode of Physics Chat, because we're not done chatting yet. I'm here with my wonderful co-hosts, Fox and Tian. On today's show, we have the amazing Tom Haworth, who researches planet formation at Queen Mary University. How are you doing?
I'm very good, thank you. Looking forward to the chat.
Oh, we're looking forward to this too. Did you do anything nice this weekend?
Yeah, actually, it was one of those weekends where I didn't have all that much on, which is a bit of a rarity in the run-up to Christmas with two kids. So just sort of getting the house in order, playing some board games. We designed some Robot Wars robots on some big A3 pieces of paper with the kids, which was really fun. So nice, quiet one, really.
That sounds so much fun. So how do you find balancing family and work as a scientist?
So obviously, it's a really big challenge. If you talk to any scientist at any level, so from undergraduate through to professors, everyone is busy. And then when you're adding in on top of that, school runs and dinner time and bedtime and things like that, clubs, it becomes a massive challenge. But I currently hold a Royal Society Dorothy Hodgkin Fellowship, which is designed to support people who have caring responsibilities and therefore need flexible working. So that enables me to do things like, in my case, I every other Monday look after my youngest son and take him to clubs, and I go home early and cook and stuff like that. So it gives you a bit of power to have the flexibility that you need. And it's a pretty unique kind of fellowship. I'm not aware of anything like that anywhere else in the world. So it's something we should be proud of having in the UK. And as for the name Dorothy Hodgkin, so Dorothy Hodgkin was an amazing Nobel Prize winning chemist. And her work included things like studying the structure of penicillin. And she was the first and only British woman who's won a Nobel Prize in the sciences. So a really amazing person.
Yeah, it's reassuring to hear that you're able to support your family and have an academic career. That's really nice to know that that's available to people. Please, could you tell us briefly about your research?
So if I had to choose one main question that I'm trying to answer, it's trying to understand why planets that we're finding around other stars are really diverse. In particular, I'm trying to understand how the environment that you try and make planets in can affect the planets that you get. That's the sort of two-sentence summary of what I'm interested in.
Hey, that's very interesting. So could you go into a little more detail about what these disks are? So we know they're called protoplanetary disks. Could you explain those in more detail, please?
Yeah, so if you took a simple picture of how you make a star, we normally think of a cloud that gets so massive that gravity can squish it down. But nothing is ever completely still. It's always going to be spinning just a little bit. And so as it collapses, what is going to happen is it's going to start to spin faster. There's a classic example of a ballet dancer or a ice skater who pulls their arms in as they're spinning, and they start to spin a lot faster. So that's going to happen as our cloud collapses. It's going to start to rotate as well. And so what happens is gravity can squish the cloud really easily in the direction that it's not rotating, but that rotation has a centrifugal force that opposes the squishing in another direction. So you end up with a star with a flattened disk around it that is rotating. And so that's why you get a disk and not like a sphere of gas around stars. And that disk is made up of two main components. It has gas in it, and it also has tiny little solids like grains of sand that we call dust. So those are the two main constituents. And it's those bits of dust that will stick together and start making bigger and bigger solid bodies that will eventually go on to be things like rocky planets and the cores of giant planets.
Very interesting. We actually have a previous video where we talk about AGN, but also dust. So if you want a further explanation of what this dust is, please go and check out Ben's AGN video. Back onto this topic though. So how common are these disks in the universe? How often do we observe them?
So we think pretty much, if not all stars are going to have had a disk at some point, but they don't last that long. So the sun is something like 4.6 billion years old. Whereas these disks, we typically see they only live for about 3 million years. So it's really only early on in the lifetime of a star, when it's a baby, that they have these planet-forming disks of material around them.
Amazing. These must be basically nothing on a cosmological timescale.
Yeah, you do get sort of what we call debris disks that last a lot longer. So a bit like the asteroid belts that we have in the solar system. So stuff that's left over, but it's sort of much lower mass disk around the star. So, but the main thing only lasts a short time.
Interesting. And you talked about in your introduction how stars affect these disks. So could you go into more detail about those effects, please?
Yeah, so there's various ways these planet-forming disks are influenced. So they can be influenced by the star that they orbit. So you've got the star and then the disk around it, sort of like it's wearing a tutu. That's where it's trying to make the planets. And the star accretes some material from the disk. So that means the star grows more massive. It eats up some of the material. And the star that the disk orbits can also shine light on it and drive what we call a wind away. So it heats the material up and makes it lose material. So that's just the star that the disk orbits. Now, stars actually form in large groups. They're not born on their own. They typically are formed in groups of hundreds or thousands or even sometimes tens of thousands of stars all together. And so what I'm really interested in is those other stars in this cluster of baby stars and what they can do to the disk. So there's two main things. One is they can fly past and gravitationally affect the disk. And that can also maybe kick out baby planets and things like this. And the other thing, which is what I'm really interested in, is that these big clusters of stars can include very massive stars. And massive stars emit a lot of ultraviolet light. So if you took the sun and copy-pasted it 40 times in the sky, the amount of UV light you'd have would be 40 times bigger than the sun normally emits, right? So you'd need, factor 200 sunscreen, 2000 sunscreens, rather than factor 50. But if you took those 40 suns and smushed them together to make one massive star that's 40 solar masses, it emits sort of tens of trillions of times more UV light. So massive stars emit way more UV. And what that does is completely blast these planet-forming disks to oblivion, right? They just lose all of their material very fast and get shrunk down. So if you put a planet-forming disk near a massive star, you have less material to make planets, the disk gets smaller, and you have less time. So really how this links into my question is, if you took two identical stars with two identical disks and put one in a nice calm environment and one in a harsh ultraviolet light environment, would you get two very, very different kinds of planets that end up?
But I have a question is why do we observe some rocky planets in solar system we have Mercury, Mars, and Earth, and also lots of gas giants like Jupiter? How do these different planets form?
So that's a good question. And it's important to note that although I'm thinking about the environment, actually still the details of how you form the basic planets themselves are still not that well understood. And areas of active research. To make the terrestrial planets, the rocky planets, you somehow have to grow your small grains of sand, your dust, up into larger bodies. And we run into various problems there. And so we can quite easily understand how small bits of dust stick together. But once they reach a certain size, they actually stop moving around with the gas in this disk. So the gas is just orbiting around, and the little blocks of sand, little blobs of sand, are also orbiting around. And once the dust gets big enough, it starts to actually feel some drag from the gas. So like the gas is bumping into it, and that causes the dust to drift inwards towards the star. So one of the ways we think the terrestrial planets, the rocky planets, are made is you get all of this sort of rain of small dust moving in through the disk, and that can be collected by sort of the seeds of planets in a region and help them grow to be rocky. If you happen to make a rocky core that's big enough, it can then start to very greedily start accreting, taking the gas from the surrounding disk and getting a big atmosphere. So that's sort of why you get one or the other, either rocky or very gassy. It depends on how big you manage to make this inner core. It also depends on where in the disk you're trying to make the planets. In the inner regions near the sun, there isn't as much material as further out. So giant planets typically, we think, form further out, rapidly assemble a big core, and then eat up lots of gas as well. So the short answer is it's quite complicated, and there are lots of different ideas about how you make terrestrial and gas giants.
From your answer, we can get conclusion is the rocky planets usually formed closer to the central star, but the gas giants usually a bit further. But we have also heard some concept called hot Jupiter before. It's a gas giant that is very close to the sun. How does that form?
Yeah, so that you already hinted at a bit of a complexity there. When we were looking before we discovered any planets around other stars, people were trying to understand planet formation purely in terms of what we see in the solar system, so inner rocky planets and outer gas giants. And so when we started finding planets around other stars and we're predominantly finding massive things close to their star, it was a bit of a surprise. It turns out we were finding those just because they're the easiest to see. So yeah, a key complication in understanding planet formation is the planets don't stay where you put them. In particular, the massive ones. So once they get big enough, they can start to interact with the disk and sort of technically would say they'd exchange angular momentum with the disk, and that can help them move inwards. Sometimes they can even move outwards as well. So the thinking is for the hot Jupiters that they formed probably further out, and then the word we would use is migrated inwards to the inner disk.
So now it's time for the most important question of all. Is there life on other planets?
I have no idea. Maybe. I mean, I'm optimistic that there could be. But one of the things we've been doing here recently at Queen Mary is starting to think about the idea of photosynthesis on exoplanets, which is a really fun project that I've been doing with a colleague called Chris Duffy, who's based in biology here at Queen Mary. And it's grown from one of these sort of funny little conversations about, well, wouldn't this be an interesting thing to look at, to actually quite a serious piece of work we're doing now. So we have a couple of PhD students and a postdoc and a grant to fund them, and we're applying for further grants. So sort of one of those instances of almost pub-like discussion turning into something a bit more serious, which is nice.
So what exactly is photosynthesis?
I am the astronomer in this astronomy biology partnership that we've got going. So apologies to any biologists that are listening. But generally, you can consider photosynthesis as being the process of turning light into sustenance for an organism. So what we would have learned in school is what we would call oxygenic photosynthesis. So that is where something like a plant or bacteria are taking water, using the energy from light to break that water apart, giving you some electrons and some protons, and those go forward to undertake chemical reactions with other species like the carbon dioxide that produces carbohydrates, and that is the energy that the plant uses. And I'm going to mention one of the slightly different type of photosynthesis that we don't normally learn in school, which maybe will become important further in our line of discussion. So the oxygenic photosynthesis needs visible light. It needs light between 400 and 700 nanometers, so the colors of light that our eyes see. And that's because if the light was redder than that, had less energy, it couldn't break the water apart that we just said was needed. But other forms of life have evolved ways of using photosynthesis that can use redder light. And so we call this anoxygenic photosynthesis. And there's a really neat example of this down on the ocean floor. So at depths beneath the ocean where our eyes actually could detect nothing. It's below, the light from the sun is so faint that our eyes just would see absolutely nothing at all. But you have hydrothermal vents, which are quite warm, and they glow in the infrared. And so you get little bacteria that can, instead of breaking water, can break hydrogen sulfide that comes out of these vents. And they use the light, just this infrared light from the warm vents to do that. So photosynthesis can take different forms, and it's not always the form that we think of when we look out my window here and see a tree. Why focus on photosynthesis? Well, it's got to be the foundation of pretty much any plausible ecosystem. You look at our planet, the dominant source of energy input into the Earth is from the sun. It's the bottom of the food chain, right? It's what the plants use, what the bacteria use, which feed the next levels of the food chain, and so on and so forth, up to us. And so for any other planet around any other kind of star, that same general idea of the main energy coming in is going to be from the star that it orbits. Any planet, at least, that we think is even remotely likely habitable. And there's some really interesting complications when it comes to photosynthesis. So we already just said that it normally on the Earth works with visible light, but most stars are actually cooler than the sun, that they're lower mass and they are redder. And so there's a question of, if you put a planet that was exactly like the Earth, had the same temperature, had the same nutrients, had the same everything, around a star that was redder, what would life look like? Would photosynthesis be able to work? Would life have to adapt in certain ways to deal with that different light? Maybe it will be anoxygenic rather than oxygenic, this life on the ocean floor using these hydrothermal vents. So this is why we're focusing on photosynthesis at this stage. It's going to be the important foundation for any other life, you'd think, on a habitable planet.
So is that possible that by using the current facility we have, that we can observe a feature in the exoplanet, that once we observe this feature, we can know for sure that, okay, there is a life or plants or animals on that planet?
So we are now already able to probe the atmospheres of planets, and we do this with instruments like the Hubble Space Telescope, the James Webb Space Telescope. And the way we do that is with something called transmission spectroscopy. So you have the star, and a transit is when the planet passes in front of the star. So that's a great way to detect planets, because you can look for the star every now and then getting a bit fainter as the planet gets in the way. Now, in transmission spectroscopy, as the planet goes in front of the star, you basically look at different phases of that process, and you can isolate when the light is going through the atmosphere. So you sort of get the light through the atmosphere, and it takes a signature with it of what was in that atmosphere. So we can do that now, and we can look for what we would call biosignatures, look for signs of life. It's going to be very difficult to find something that is unambiguously agreed upon by all as having been due to life. There's a classic example of why this would be strongly debated. If we look at Venus, the atmosphere of Venus, there was a claim of a phosphine detection, or there is a fairly convincing phosphine detection in the atmosphere of Venus that was discovered in recent years. But the actual source of that has been very strongly debated. So you had a team suggesting it had to be due to life, others saying it had to be due to volcanism, others just saying we don't understand the chemistry of phosphine very well. So I think it's going to be very unlikely that we see something and everyone goes, "Yep, that's definitely life."
So is there a possibility that the feature we're looking for to determine photosynthesis is uniquely from life, or could it also be from another source?
For photosynthesis specifically, there is one possibility. So something called the red edge. So plants, trees are very, very reflective at a wavelength of 700 nanometers. So what would be the red end of visible light? And we have to deal with that when we build things like satellites that orbit the Earth. If they've got a detector that's looking at the surface of the planet that's very sensitive, then it can be damaged by the 700 nanometer sort of high reflectance if you're not careful, or have some sort of interference. So yeah, that red edge has been suggested as something we might look for to search for signs of photosynthesis happening on other planets. So a high jump in how reflective the atmosphere is, or the planet is at those wavelengths. I think to boil down my answer so far, we have the tools to probe the atmospheres, but we don't really know unambiguously what to look for.
If there were trees or plants on other planets, what color would these plants be? Would they be green like Earth?
Yeah, so actually plants or whatever form of life you might have could be green on other planets, but they could also be other colors too. So one of the things that I've really enjoyed about this project and working with Chris Duffy from biology here is learning more about why plants are the way they are as well. So having discussions about how they behave when they're put under stress, when they've not got enough water or overexposed to light, curling up their leaves and things. And one of the things I hadn't really appreciated is why plants are green. So we said earlier that they absorb visible light, so from 400 to 700 nanometers in wavelength. But they don't actually do that across that whole range. They have what we call pigments in them that do the absorbing, that actually take the light. And they do that at the blue end of the visible range and at the red end of the visible range. Okay, so there's a gap in the middle. So they absorb the blue and the red, and what you're left with is the green in the middle. That's the reason that they look that way. But the cyanobacteria and other kinds of bacteria as well can absorb a much wider range of wavelengths. So some of them look black, others look purple. So you have purple cyanobacteria. So yes, you could have green life forms, but you could also have these darker ones as well. And in fact, in the work we've done so far, purple cyanobacteria seem pretty well adapted to life around these redder stars. So might be more like purple.
Wow, this leads me nicely on to my favorite part of the show, my random question. What is your favorite tree, flower, or plant, and why?
Okay, I would have to go for an aster, which is a kind of flower with star-shaped petals, and the name aster is ancient Greek for star.
That's so cool. I'd never seen that before. What about you, Fox?
Well, I had a book as a child which had like little fairies and poems about different types of flowers. And I thought the nicest poem in there was for bindweed. So that shows you how much I know about plants.
That is hilarious. What about you, Tian?
I don't have a specific favorite, like plants, trees, but I do enjoy sitting under any kind of big trees, as long as they're big.
Well, my favorite flower is a lily because my name is actually Hebrew for lily. Well, thank you so much, Tom, for being on Physics Chat. It's been so interesting hearing about your research and learning about how stars impact planet formation. Also, hearing about whether we can find life on other planets. Maybe one day we find a tree on another planet. Who knows? And maybe that tree is a black tree. It sounds so cool, but thank you so much again for being on this show. Let us know in the comments section what your favorite tree, flower, or plant is. We would love to hear from you, so keep writing. But from everyone at Field of View, we hope you have a great day and goodbye. Bye.
Bye.
I think it's going to be very unlikely that we see something and everyone goes, yep, that's definitely life.